In this lesson, we will discuss projective and affine planes, which are two of the most important examples of incidence geometry. During the Renaissance, artists developed a theory of perspective in order to realistically paint two-dimensional representations of three-dimensional scenes. This theory described the projection of points in the scene onto the canvas by lines from those points to a fixed viewing point in the artist's eye, and the intersection of those lines with the plane of the canvas was used to construct the painting. The mathematical formulation of this theory was called projective geometry. And in this technique, all the parallel lines that lie in a plane cutting the canvas are painted as meeting at one point, and they meet at a point at infinity on the horizon somewhere in the painting. Here's an example of projective geometry in Renaissance paintings, The Last Supper by Leonardo da Vinci. And we can see that there's many parallel lines in this two-dimensional rendering of a three-dimensional room, and the parallel lines seem to converge to a point in the distance on the horizon. If we look at this sketch, we can project all the parallel lines that are in the painting, and we see that they all converge on the horizon at the line of infinity at a single point, which is actually directly behind Jesus. So it makes him the focal point of this painting. So in this model, you see that parallel lines actually meet at a point in infinity. Now we have the elliptical parallel property in this extended plane. So we're going to look at this, how we can extend the idea of a Euclidean plane where the Euclidean parallel postulate holds into what we call a projective plane where the elliptic parallel property. First, let's remind ourselves of the incidence axioms because our models of incidence geometry here are going to still satisfy these incidence axioms. First, for every point P and for every point Q not equal to P, there exists a unique line L passing through P and Q. We have that for every line L, there exists at least two distinct points on L, and there are three distinct non-collinear points. So there exists three distinct points that no line is incident with all three of them. Our models, called projective and affine planes, still are incidence geometries, so they satisfy these axioms. And recall the three parallel properties. We're going to see the elliptic and Euclidean properties in this lecture. The elliptic property states that for any line L and every point P not on L, there are no parallel lines passing through P in parallel to L. The Euclidean parallel property states there's exactly one line parallel to L passing through P, and the hyperbolic property says that there are at least two, so there's more than one line parallel to L passing through P. So we're going to primarily look at models with elliptic and Euclidean properties today. First, let's start with some definitions. A projective plane is a model of incidence geometry, so it still satisfies the incidence axioms. It's an incidence geometry having the elliptic parallel property, so that every two lines meet. There are no parallel lines in this model. Now, further, we're going to stipulate that every line in a projective plane, this model of incidence geometry, there's at least three distinct points lying on it. So recall that axiom 2, the incidence axiom 2, established the fact that there's two distinct points lying on it, but now we're going to strengthen that. We're going to call this the strengthened incidence axiom 2. So a projective plane is a model of incidence geometry with the elliptic property, elliptic parallel property, and satisfying the strengthened incidence axiom 2. An affine plane is going to be another model of incidence geometry having the Euclidean parallel property. So we satisfy the three incidence axioms, and the model has the Euclidean parallel property. Recall from our last lecture, we looked at this example of 4-point geometry. So it's a finite geometry, only 4 points, A, B, C, D, and the lines were subsets containing exactly 2 of the points. There are 6 lines, and we said that incidence was defined as set membership. So for example, point A is on the line, which is the set containing A and B, and so on. So below, we see a visual representation of this 4-point geometry. And we can verify that this model has the Euclidean parallel property. So as a model of incidence geometry with the Euclidean parallel property, that is the definition of an affine plane. And in fact, this example is the smallest possible affine plane. You can't have any smaller set that's isomorphic to anything smaller than this set containing 4 points. Now, another visualization is this more triangular formation, and this is a nice representation because the whole model is represented in a two-dimensional plane. We still have, it doesn't matter which point you label A, B, C, D. So we're going to use this picture because it'll help us make a projective plane from this affine plane later when we talk about projective completions. And before we move on, I want to talk about some set theory. In particular, I want to talk about equivalence relations. So equivalence relations are pervasive in mathematics. I use them a lot when I teach abstract algebra. Equivalence relations are very important in mathematics. So let's recall what a relation is, first of all. Let's call a relation, and we use the symbol tilde in between two elements of a set A. So a relation on a set A is a subset of A cross A. So A cross A would be the set of ordered pairs, A and B, A comma B, where A and B are elements of A. So we say that A is equivalent to B, or A is related to B, if AB is in this relation. Okay? A relation has different characteristics. One thing a relation can be is reflexive. So we say a relation on A is reflexive if A is related to A for all A in set A. A relation is symmetric if A is related to B implies that B is related to A for all A, B, and A. And then a relation is transitive if A is related to B and B is related to C implies that A is related to C for all A, B, C, and A. So an equivalence relation is a relation that is reflexive, symmetric, and transitive. So once we have a relation that defines an equivalence relation, then the equivalence class of an element A in set A is a set of all elements in A that are equivalent to A. So now when we have an equivalence relation, instead of saying X is related to A, we'll say X is equivalent to A. So if we look at the set of elements of A, set of all X in A, such that X is equivalent to A, that is a set, and that is called the equivalence class of A. And equivalence classes are important. One powerful use of equivalence classes is the fact that equivalence classes partition the set A. So that means that every element of A is in exactly one equivalence class. So these are subsets of A that that cover the whole set A, but no element is in more than one equivalence class. So we say the equivalence class is partition A. This is a useful property of equivalence classes. So we're going to need to use equivalence relations to get from an affine plane to a projective plane called the projective completion. So we're going to start out with an affine plane A, and we're going to define a new model of incidence geometry that adds points and adds a line to an affine plane and makes it into a projective plane. So we're going to describe this process, but the main idea is we're going to add points at infinity to an affine plane. So we'll define what that means in a minute. And we'll add one line to the lines of an affine plane. And this line is going to be called the line at infinity. And it's important to understand that our models are abstract math definitions. It's an abstraction of mathematics. So we have to make sure we're not just thinking of geometry as in the Euclidean sense of a straight line, a point on the line, and then a point line on a line defining incidence. Remember, we can choose any way we want to define points, lines, and incidence in order to define a model of incidence geometry. As long as our definitions and our sets and our elements all satisfy the incidence axioms, then we still have a model of incidence geometry. So this is going to be important that we're going to add points at infinity that are actually sets. And our line at infinity is actually a set, but it's still going to satisfy the axioms of incidence geometry. So let's assume that we have an affine plane, capital A, and we're going to define a relation tilde on the lines of A. And here's how we define it. We'll say that L is related to M, and we'll see this is actually an equivalence relation. So L is going to be equivalent to M if and only if L is equal to M or if L is parallel to M. That's how we define the relation. We're going to show that this is actually an equivalence relation. We need to show three things: reflexive, symmetric, and transitive. Let's do that. Let's show this relation is an equivalence relation. So here's the definition of the relation here in the box. But first, I'm going to show that this relation is reflexive. So I need to take any element L of A, of the affine plane A, I need to show that L is related to itself. Well, since L equals L, that means that L is related to itself. So reflexive is pretty straightforward, pretty easy. Symmetric is pretty easy as well. So suppose that L is related to M. So we have two possibilities. If L is equal to M, then we know that M is equal to L, and we can conclude that M is also related to L. But if we assume that L is parallel to M, then we know that means that M is also parallel to L, and therefore, again, M is related to L. So we have the fact that this relation is symmetric. If L is related to M, then M is related to L. All right, let's talk about transitivity. So let's suppose that L is related to M and that M is related to N. So these are three lines, L, M, and N. And we need to show that L is related to N, show transitivity. Well, if any pair of these lines are actually equal, then clearly L is going to be related to N, just by what we did in the symmetric and reflective cases. So we can assume that all three of these lines are distinct. Okay, so we don't have to worry about the case when L equals M or M equals N or L equals N. So we're just going to deal with the possibility that all three lines are distinct and L is parallel to M is parallel to N. So again, these are three distinct lines with all these parallel relations. So we need to show, so to finish transitivity, we need to show that L is parallel to N. So let's assume to the contrary. So suppose to the contrary that L intersects line N at point P. So that would be the opposite of L being parallel to N. Well, we're still assuming that L is parallel to M. And since L is parallel to M, P does not lie on line M because we assume that P is on line L. But then that leads us to two distinct parallels to M, line N and line L, that pass through point P. And this contradicts the Euclidean parallel property of the affine plane A, which states that there's exactly one line parallel to M through P. So this is a contradiction. So we can conclude that L is parallel to N, and that finishes transitivity. We know now that L is related to N. So this is an equivalence relation. So now we're going to look at equivalence classes defined by this equivalence relation. These equivalence classes are going to be important for extending an affine plane to a projective plane. So the equivalence class of L, we'll denote it by this symbol where we have square brackets around L. This is a set, the set of all lines that are equivalent to L. So the equivalent class of L equals the set of M, the lines M and A, such that M is equivalent to L. So again, remember that means that there's a set of all elements, all lines in the affine plane A that are equal to L or parallel to L. So the equivalence class of L is the set containing L and all lines in A that are parallel to L. So think about the affine plane with the standard Euclidean plane when viewed as an incidence geometry model. Equivalence classes are essentially parallel classes. So all the lines that are parallel or equal are in one equivalence class. So for example, vertical lines are one equivalence class. The set of all vertical lines would make it one equivalence class. Similarly, the set of all horizontal lines would be an equivalence class. You could define an equivalence class of all lines that have slope 1 or all lines with slope 2 and so on. So these are all kind of parallel classes in the standard Euclidean plane, Euclidean model of an affine plane. So the beautiful thing about equivalence classes now is that we had equivalence where we had L is equivalent to M, but now we're taking from equivalence to an equation. We have equality now when we say the equivalence class of L equal to the equivalence class of M. That means that L and M are either equal or parallel. So these equivalence classes are going to be points at infinity that we're going to add to our affine plane. So these equivalence classes are called points at infinity. So this is, again, an abstraction of what a point can be. So a point can be anything that we define it to be as long as that model satisfies the incidence axioms. So if we take all of these equivalence classes, all of these points at infinity, we can join them together into a set, and we're going to call that the line at infinity, denoted L infinity. So this is going to be the set of all points at infinity. It's going to be the set of all equivalence classes of lines in our affine plane. So with these definitions, we can now talk about how to extend an affine plane to a projective plane. So our new model is going to be called A star. So A is an affine plane. And we're going to define our new model, A star, by taking all the points that are in A and adding to that all of the points at infinity. So the regular points, the ordinary points of A, are the points that are inherited that were already in the affine model A. We're going to call those ordinary points. And to distinguish them from these equivalence classes, which we're calling points at infinity. The lines of A star are going to be all the lines of A plus one more line. It's going to be the line at infinity, L infinity, which again is the set of all points at infinity. We still have to define incidence. So incidence in our new model, A star, will be defined as incidence of ordinary points the same way they were incident in model A. We're going to inherit the incidence of ordinary points with each other and with the points and lines. Now we're going to extend this definition of incidence to state that each equivalence class, each point at infinity, lies on every one of the lines in that class. So we're going to say, for example, the equivalence class of L lies on line L and on every line M that is parallel to L. So note that in the affine plane A, if L and M are distinct lines that are parallel, they don't meet. But these lines will meet in A star because the equivalence class of L lies on both lines L and M. So now we see that we no longer have any parallel lines in our model A star. So that gives it the elliptic parallel property. Well, this new model A star is actually a projective plane called the projective completion of A. So given any affine plane A, we can use this extension by adding points at infinity, a line at infinity, and increasing the incidence relation to obtain a projective plane, a new projective plane, and this is called the projective completion. So we're now going to prove that this model is actually a projective plane. So we have to show that it satisfies the incidence axioms, but also including the strengthened axiom, incidence axiom 2, along with the elliptic parallel property. So to prove that A star is a projective plane, let's verify the incidence axiom 1, which states that for any two distinct points, there's a unique line passing through them. So if we let P and Q be ordinary points, we know that incidence axiom 1 already holds in the affine plane A. So we know that P and Q lie on a unique line of A, and they do not lie on L infinity. If we had an ordinary point P and we let Q be an equivalence class, so a point at infinity, let's say the equivalence class of M, then we need to show that there's a unique line passing through P and Q. Well, if P lies on line M, then the line PQ is equal to M. If P lies on a unique line N that is parallel to M, which we know exists by the Euclidean parallel property, so if P does not lie on M, then it lies on a unique line parallel to M. And since N is parallel to M, N and M are in the same equivalence class. So Q also lies on line N. Therefore, the line through P and Q is equal to N. And either way, we have a unique line passing through P and Q. What if we had two distinct points that are points at infinity? Well, the way we defined L infinity, both of these points lie on L infinity, and therefore the line passing through P and Q is equal to L infinity. So every two distinct points in a star have a unique line passing through them that verifies incidence axiom 1. To show the strengthened incidence axiom 2, we need to show that there's at least 3 distinct points on every line of a star. So if we started with M, which is a line in the affine plane A, and we know by incidence axiom 2, which holds in A, that M has at least 2 points lying on it. The way we define incidence, we said that the equivalence class contained M lies on line M, so that is going to be our third point. So we have 2 ordinary points, and we know at least 1 point at infinity is on line M. So if we had L infinity as our line, we need to show that L infinity has at least 3 points on it. So consider the 3 lines that join the 3 non-collinear points that are guaranteed by incidence axiom 3. These 3 lines, let's call them L, M, and N, they intersect in pairs. No 2 pairs of these lines is parallel. So they're representatives of 3 different points at infinity. Equivalent class of L, the equivalence class of M, and the equivalence class of N. So these 3 distinct equivalence classes represent 3 distinct points, all lying on L infinity. So that shows that every line in a star has at least 3 distinct points lying on it. That's strengthened incidence axiom 2. Next, we are going to show that a star satisfies incidence axiom 3. And it shows that there's at least 3 non-collinear points in a star. But incidence axiom 3 already holds in the affine plane A, and all the points of A are also points in a star, so there's at least 3 non-collinear points in a star. The last thing we need to show is that A star is a projective plane and therefore satisfies the elliptic parallel property. If we had 2 ordinary lines that are parallel in A, then we saw that they belong to the same equivalence class, and so they intersect at that point at infinity. That point at infinity lies on every line that's parallel, so these 2 lines will intersect in A star. If I start with an ordinary line M and consider the line at infinity L infinity, we see that M and L infinity meet at the equivalence class of M. Therefore, there are no parallel lines, and we can conclude that A star is a projective plane. So given any affine plane, we can create a projective plane. Well, if we took a projective plane and we get rid of this line at infinity and all the points that are on it, then we could get from a projective plane back to an affine plane as well. So recall our 4-point geometry model. This is a visualization of the 4-point geometry and all the incidence relations. This model of incidence geometry we saw is an affine plane. This is the smallest affine plane. So now let's look at a visualization of the projective completion of 4-point geometry. What it's going to give us is actually the smallest projective completion, smallest projective plane. So this is a visualization of the projective completion of 4-point geometry. It's the smallest projective plane. We can verify that of all these lines, every line has at least 3 points on it, and there are no parallel lines. So this is the smallest projective plane. And we can think of the circle in the middle as the line at infinity, and the points that lie on the circle are the points at infinity. Now, this model is often called the Fano plane because in honor of Gino Fano, who worked with finite geometries in 1892. So this is a visualization of the smallest projective plane. So let's now talk about the projective completion of the real affine plane. When we look at the Euclidean plane as a model of incidence geometry, so as just satisfying the incidence axioms, we call that model the real affine plane. Its projective completion is called the real projective plane. So we're going to try to visualize this projective completion. So to do that, let's think of the Euclidean plane as this horizontal plane T. So that is the Euclidean plane. We take the Euclidean plane T and make it tangent to a sphere centered at the point O and tangent at its north pole. We're going to call that point the north pole N. Then this will help us visualize the real projective plane. So we have a point P in T. It's going to correspond to a point P prime in the northern hemisphere. And the way we're going to correspond them is by drawing a Euclidean line, a line that passes through the center of the sphere O and the point P in the Euclidean plane, and it's going to pass through exactly one unique point in the northern hemisphere. So we're going to call that P prime. We have a one-to-one correspondence between points in the Euclidean plane and points of the northern hemisphere. The point N will correspond to itself.
Similarly, given any line M of T, we can join M to the center of the circle O by a plane called pi through O that cuts out a great circle on the sphere and a great semicircle, we're going to call this M prime, of the northern hemisphere. And this correspondence preserves incidence. Now suppose we had 2 lines, L and M, that are parallel in T, then the planes through O, determined by these parallel lines, will meet in a line lying in the plane of the equator. A line that, since it goes through O, it cuts out a pair of antipodal points on the equator. So that's 2 points that are on opposite sides of the equator. So we can think of the line of infinity of this projective completion as the equator of the sphere S with antipodal points on the equator pasted to each other. So therefore, the real projective plane can be visualized really only partially because we can't really visualize this pasting of antipodal points together. But we can think of the real projective plane as the northern hemisphere with antipodal points on the equator pasted to each other.